Hello calculus class. We're viewing this video after class on Monday, so that's the 26th. And we've been reviewing for quite a bit, and I've run out of review questions. So we're going to go make some forward progress, and this will not be on your test. Today we're going to look, our goal is to find the slope of the line tangent to a graph at a given x value. So let me sketch an idea here. So if we have a graph, so we don't have a straight line, so we have a curved line, and say we're interested in the point, this given x value. I was wondering what the slope is of that tangent line at that point. A tangent is a straight line that touches the curve in one point and does not pierce the curve near that point. So right now we don't know how to do that, but there'll be a lot of information if we did know the slope of that curve, which we'll come to appreciate as time goes on here. But what we could do, let's start with something we could do. We'll draw a straight line through 2 points actually on the curve itself. So when I do that, I can find the graph of that, because this point I'll call x, and this point we'll say will go up to x plus, say, another value. Say the distance between this and this is h. So we'll have x plus h. And then corresponding, if this value is x, then this point here, so y value is f of x, and this point here, the value for y is f of x plus h. Alright, so if I was doing the slope again from these 2 points that are actually on the curve, anything on the curve I can find its name. So I'm going to do a rise over run, and this straight line that cuts through the curve in 2 points is called a secant. It is not a tangent. So at this point, the actual slope of the secant, the rise part of f of x plus h, this value from here, from the x-axis to here, is f of x plus h. But I'm only interested in this section. But from here to here is f of x. So how will I get just the part of interest? I will subtract the f of x plus h, subtract from f of x plus h, f of x. So, and then I'll divide it by this value, which I said from x to x plus h is h. Do you feel like bursting into song? So this is the slope of the secant. F of x plus h minus f of x divided by h divided by h. This is the blank blank. Do you recall what that's called? It is called the difference quotient. Okay, I hope no one in your house heard me singing. Alright, so how can this help us go from the slope of the secant to the slope of the tangent? Well, it turns out that if I push this point along my curve closer, and I create the secant, here's the tangent line, right there. And if I create the secant here instead of the first place I showed you, instead of up here, how is that progressing toward the tangent slope? Well, you can see that it's all closer of a slope than in the first exercise where we use this point. So if we did change x plus, if we made, instead of having our value of h that big, if we shrunk it to here, x plus h is now only this big. And when we do that, our f of x plus h comes down to here instead of up here. And everything is shrinking. And we have f of x plus h minus f of x, this value, and where it was this value. And h was this value, and now it's this value. So you can see as I choose a point closer and closer to the point of interest where I'm establishing my tangent, the sides shrink and shrink and shrink until in the limit land, we could have the h actually go to 0. So when we have a secant, we can have it approach a tangent line by taking its limit. So let's take the limit of f of x plus h minus f of x divided by h. And I didn't fill in the limit as what goes to what. Can you envision what that would be as I'm describing this process of getting closer and closer to the tangent line from the secant line? This value h is directing the whole thing. As h shrinks to 0, we do approach the tangent line. So the limit of the secant is the tangent line. So we can actually find the slope using a limit definition. So let us do that for an example. Let's do one that we could know anyway. Let's take a function. We already know the slope of this. F of x equals 2x minus 3. So we already know that's a straight line. It crosses the y-axis at minus 3 and has a rise over run of 2. So if we drew any tangent line, it would be the actual line itself. And we know that the slope everywhere is 2 on this graph. But let's use the limit definition to prove the obvious, just to prove that it works. So I'm going to take the limit as h approaches 0 of my function is f of x equals 2x minus 3. So what would f of x plus h look like? Well, everywhere there's an x, I'm going to substitute an x plus h. So I'm going to get 2 times x plus h minus 3. So that's this part. Now I hit the minus sign. And the function will follow it. The function is 2x minus 3 over h. All right, let's simplify. In the numerator, we will have 2x plus 2h minus 3 minus 2x plus 3 all over h. The fun part. So we get the limit as h approaches 0 of what's left here, just a 2. Since there's no h in that expression, the limit is just 2, which we expected. All right, let's do one that's a little more interesting than that. I don't know if I can fit it on my paper, but I'll give it a try. All right, I'm going to do the limit as h approaches 0 of, well, let me give you the problem first. I think I will need another piece of paper, so. And even though I got my phone, I failed to turn it on. So what else is new? Let me go ahead and shut this down. I don't want to go over, and I don't think I have, but I'll make it a 2-part, 2 short parts. So, be right back, part 2.